All right, this is a train wreck. Let's give this train wreck a chance. Okay, I'm not sure this is going to work. Oh, let me record the Zoom. All right, guys, let's stand up. Let's stand up. Let's stand up. Let's stand up. I don't know why I'm not the speaker. Oh boy, here we go. Let's sit back down. Let's sit back down. Can you hear me? I don't know which it's recording. Okay, hold on here now. So I forgot my iPad today. I forgot my iPad and my tripod. So right now I have my phone leaned against a chalkboard to record. And I'm trying to record the Zoom meeting also so that that will be available. But right now I'm just seeing Luke's face. Right now all I've got is Luke large. And so he's not lecturing. So I'm going to try to make my face show up here as the... All right, I just got to believe that, I just have to believe that the camera is going to record as good as possible because I don't know if I'm going to be able to get this recorded right. I guess we'll see, Okay, what I want you to do is I want you to write down, the following lines. I want you to write down the following lines. Okay, so the first line, when I say line, you say, when I say line on Friday, you say
A plus T.
A plus TD. So if I'm looking at this line, I'm going to make this a little bit easier. I'm going to put some zeros in here. I suppose I've got 1, 2, 3. That's my position vector. TD is 2, 0, 4. So there's my first line. Now I've got my second line, which is like 1, 1, 1, plus T times 0, 1, 3. Now, if you saw that on Friday, if you saw those two things on Friday, how many people would be able to recognize that those are in fact 2 lines? How many people can recognize that those are 2 lines? Okay, now if I have 2 lines in 3-dimensional space, there's 3 options. They can intersect. That's rare, but they could intersect. They could also be parallel. Or most of the time, they're not going to intersect. They're not going to be parallel. And what do we call that kind? Skew lines. So now, we've just written these down. Now imagine on Friday, I ask you, do these lines intersect? Are they parallel? Or are they skew? And you're like, well, Dr. Warren, what do I do? What do I do? Well, I assigned some problems like this, but I just want to walk through an example because you can do it a slow way and a fast way. And I'm just going to write down the fastest way I know how to do this. Okay, if you're wondering, the first thing you want to rule out is intersecting. The first thing you want to rule out is intersecting. If two lines are going to intersect, then there's got to be a scalar that I can put in for this first line, a second scalar that I can put into the second line that is the point of intersection, that points to the point of intersection. I've got a position vector for one of the lines, a position vector for another one of the lines, that both come from the origin, and they point to the exact same place. They point to the exact same place. They point to the exact same place. And the easiest way to do this is to just set these two equations each equal to each other, and you write it down like this. You just say R1 of alpha. I pick alpha just because I run out of variables. R1 of alpha, that position vector, has to be equal to R2 of beta. There's got to be a scalar alpha and a scalar beta where these two position vectors point to the same place in three-dimensional space. Okay, now, you guys are going to do two steps at once. You're going to do two steps at once. If I evaluate R1 at alpha, where does the alpha go? If I evaluate R1 at alpha, where does the alpha go? Well, it goes wherever the t is. And here I'm evaluating R2 at beta, so it's going to go where the t is. And then what I want you to do is just write this down. Write the consequence of this down as a vector equal to a vector, just as an ordered triple. Write down the three ordered triples from the first one being evaluated at alpha, and the three ordered triples to the second one being evaluated at beta. So do that at your seats. You guys write down. What would be the first set of three real numbers that would be associated with R1 of alpha, and the second ones that would be associated to R2 of beta? And you guys, I'm looking at my phone now. I can't believe I'm looking at my phone. Okay, you guys should be doing the same thing. Okay, on Friday you should be done. By now. Okay, now I'm just recording Mason. Yeah, this whole thing, I've got to figure out how to record using Zoom. I'll go back to grid view. Okay, what do you have since I just saw Mason? Mason, what do you got, man, for me on that first component? What's this first component here?
1 plus 2 alpha.
Perfect. 1 plus 2 alpha. 1 plus 2 alpha. 1 plus 2 alpha. The 1 plus alpha times 2. Now what do we have for the second component? Then?
2.
Just 2. It's just 2. It's 2 plus 0 alpha. And then my third component, I think everybody's kind of catching on, is 3 plus 4 alpha. Similarly with the second equation, we would have 1 plus, 0 times beta, which would just be 1. Then we would have 1 plus beta times 1. And then for the last one, we're going to have 1 plus beta times 3. Now I'm giving your ears a break. Again, if two lines are going to intersect, we have to have a scalar alpha that'll position this vector to the same place a scalar beta would position this vector. Nothing's hard here. There's just a lot of writing. Now, we decided in this class two vectors are equal if and only if. We decided in this class two vectors are equal if and only if vector A equals vector B if and only if their components are equal. If A1 is equal to B1 and so on. So using that, if I look here, then 1 plus 2 alpha would have to be equal to, 1 plus 2 alpha would have to be equal to 1. 2 would have to be equal to 1 plus beta. And 3 plus 4 alpha would have to be equal to 1 plus 3 beta. Now, how many people are happy I put some zeros? How many people are happy I put some zeros in those direction vectors? Because typically, this is a system of 3 equations, but only 2 unknowns. And it almost always fails. It almost always fails. If it doesn't fail, if you can satisfy all 3 of these equations, this one, and that one, with just 2 numbers, then the lines intersect. The lines intersect. Well, let's just check here. Let's say if I'm looking at this equation would imply alpha is equal to, this equation would imply alpha's got to be equal to, you got 1 plus 2 alpha is equal to 1. That would imply that alpha's got to be equal to 0. Very good, Michael. That would imply alpha's got to be equal to 0. Looking at the second equation would imply beta's got to be equal to, looking at the second equation, beta's got to be equal to 1. Now that's fixed. That's fixed in stone. Now I come over here. Well, if alpha is equal to 0 and beta is equal to 1, does the third equation check? If alpha is equal to 0, and beta is equal to 1, if alpha is equal to 0, we get a 3 is equal to beta equals 1, 4, and that's clearly just crap. So what does that tell me about these 2 lines? They don't intersect. Okay, the next thing I'm going to ask are they parallel? We know they don't intersect, but are they parallel? Well, that would mean, are there direction vectors? What did I just say? What were the words that just came out of my mouth? I know no matter what I said, you weren't going to listen. What did I just say? Yeah, if they're direction vectors are parallel. You got 2 direction vectors, and they're parallel. Does it make sense the lines that run through them would also be parallel? Now, what's the easiest way to check whether or not two vectors are parallel? You could use the definition, that would be one way, but probably the easiest way is to take their cross product. If the cross product is the 0 vector, then they're parallel. So let's just see. You guys help me out. We're not doing the cross product. You know you're going to be doing the cross product on Friday. But what would be the direction vector of the first line? What's the direction vector of the first line? If you're looking at the first line, what's the direction vector? 2, 0, 4. So this would be the direction vector of the first line. This is the direction vector of the second line. And then you would take the one of those, Cross product. How many people like they can take a cross product? I hope the answer is yes. Now, if any one of those components in that cross product vector, is not 0, then you know the two lines are not parallel. The moment you rule out not parallel and not skewed, not intersecting, I gave the result. Then the answer has to be their Skew. They have to be skew. Does this make sense? Does this make sense? Okay. Stand up, stand up, stand up. Stretch. Okay, let's talk about Quest 2. Let's talk about Quest 2. Now that almost everybody's here. On Quest 2, there's going to be a little bit of dot. A little bit of dot product. A lot of cross product. Which is our section 12.4. Which is our section 12.4. And then there's going to be lines. What we were covering on Monday, including what I was reinforcing here, and this next thing I'm going to reinforce. The next thing I'm going to reinforce. Okay, I've decided that I don't like the logistics of you guys having to juggle both WebAssign and a handwritten. I've decided I don't want you guys having to juggle because it's 40 minutes. I've got a lecture. I don't want you having to open up two things and have to do. So we're going old school. We're going old school. It's all going to be handwritten. It's all going to be handwritten. We're going old school. Okay? Now, by old school, those who've had Dr. Warren know what old school is. Okay? Old school is you show up with a pencil in your brain. That's old school. You don't need any teddy bears to hold on to. No calculators. No calculators. You're allowed your what? What are you bringing with you on Friday? Pencil and brain. That's it. Pencil and brain. And Zoom. As far as technology, you'll need to open the PDF and you'll need to take pictures and give me your answers. I'll give you time on both ends for that. Okay? But other than that, you guys are in class taking the quest just like what you would. Okay, we're also going old school in that Dr. Warren's quests are hard. Say that.
Dr. Warren.
Okay. I consider it my job to ethically test all ranges of students. And I've got a good class. It's clear to me from my first quest and how well you all did on that first quest. Typically, my average on that material, on my first assessment, is in the 60s. And you guys were 80, okay? So that's like almost a 15-point standard deviation. I've got bright kids in here. I also have kids that maybe will need remediation. So I like to put what I call ferret questions on my test. Ferret, meaning that if you've been a ferret, zooming in every single lecture, you should get this question right. And if you're not, if somebody misses that, that's a real sign to me. Wait, there's a definite misconception. I need to meet with this student and talk about remediation. You know, so if I put on something that's reasonable, like if I say, you know, is this a line? Then I'm thinking, okay, and you're not recognizing A plus TD is a line. I'm like, whoa, you know, we're either not doing our work or I'm missing you completely. Then I like to put on questions that are like Lord of the Ring monsters, okay? And so that's what, you'll be facing a Lord of the Ring monster on Friday. You're going to face, and I want to see how you swing. I want to see how you swing that sword. Are you going to cower and drop your sword and leave it blank? Or are you going to pick up your damn sword and come at it with everything that you've got? That's what I want to know. Are you... And then, if I have a kid who knocks that problem out of the park, I know I really have to sit down and talk about this student being a math major. I don't care what the hell major you are. If you've got that much talent in mathematics, we need to think about double majoring. Okay, so I'm going to test the full spectrum of my students. The full spectrum of my students. We're going old school. What did I just say?
Old school.
We're going old school. No calculator, no technology. You're allowed your brain. Your brain. Are you allowed to bring your flashcards? No. Should you have your flashcards memorized? Yes, yes. Will the flashcards help you with the Lord of the Ring monster? Maybe. This is what's going to help you the most. How creative is your mind? How creative is your mind? There'll be two major arguments. There'll be two major arguments on the quest. One will be something that you've seen. Something that you've seen. Okay. Another one will be something you haven't seen. And that will be the Lord of the Rings. The rest of it will feel kind of like our handwritten that you've already seen. The rest of it will feel kind of like the handwritten. If you've been doing your homework, okay, you should feel pretty comfortable in things. If you know your flashcards down cold, and I mean down cold, you should be able to hit the things like throwing the true and false. Yeah, so other than that, old school, old school. Stand up again, stand up again, stand up again. Stretch, stretch. Yeah, Stuart.
Will we have the whole class period to work on it?
No, Stuart, no. I will lecture for about 40 minutes and give you 40 minutes. Okay, sit back down, sit back down. Thanks, Stuart, guys. We'll take it at the end, so those who get done first, early can get out. Okay, go to grid view, go to grid view, go to grid view, go to grid view, go to grid view. Put your hands on the space bar, put your hands on the space bar, put your hands on the space bar. Look at everybody, look at your class and say, it's going to be okay. Look at your class and it's going to be okay.
It's gonna be okay.
Say, do well, do well.
Do well.
Say, Dr. Warren controls the circuits. Yeah, okay. So yeah, I mean, guys, I'm not going to put you up on a trapeze just to like watch you fall. I mean, I'll have nets under you. I'll have nets under you. You know, but you're going to climb a trapeze. You're going to climb a trapeze. My academic trapeze. Okay, a little dot, a lot of cross lines. A little dot, a lot of cross lines. Okay, the last thing I want to reinforce that could be on the test related to lines. We talked about this last time. If I say line, you say
A plus TD.
A plus DD. If I say point, you're like, I don't know. What? Point is just three real numbers. A point is just three real numbers. So imagine that on Friday, I give you a line, A plus TD, and I give you a point, three numbers. And then I ask the scary question, what's the distance from the point to the line? What's the shortest distance from the point P to the line A plus TD? I mean, I'm hoping, the flashcards go up to, I think, 49. 49 is kind of like where we're at right now. I'm hoping that you won't have to rederive it on the quest. I'm hoping that you're not going to have to invest 5 minutes rederiving. But that's what I'm going to do. I'm going to pretend like I'm a student who's forgot my flashcard. The flashcard didn't register enough. And so I'm going to go back and visually, I'm given a line, 131 plus t times 4, 6, 2. Who's the position vector? Who's the position vector? We got to at least know this. Who's the position vector?
131.
131. And who's my direction vector? Who's my direction vector?
462.
462. This is my A, and this is my D. Now I'm also given a point. I'm given a point in three-dimensional space, so I'll just say maybe it's like 2, 1, 7. And let me just say, guys, not having a calculator is a blessing, not a curse. Not having because that means I've got to pick numbers that make it simple so you don't have to need a calculator. So I'm really testing the theory far more than can you actually multiply, add, subtract, and divide. I mean, like over here, I put a bunch of zeros in. I don't need to see, can you solve a system of two equations, two unknowns? That was all of high school. I need to know, do you understand when two lines intersect, geometrically? Okay, so now I'm asking, what is the shortest distance from this point to this line? And you're like, crap, I forgot that flashcard. I don't know, how do I do this? Well, let's just rederive it reasonably quickly. I would sit myself in three-dimensional space. This would be the which axis? This would be the which axis?
X.
Y. And then I've got my line. I've got a position vector, maybe A. You know, I shoot it up like this. my position vector A, and maybe I've got a direction vector heading in that direction. I've got a direction vector heading in that direction. Now the line is going to run along the what? That line, visually in three-dimensional space, the line's going to run along what as we draw this out? Yeah, it's going to lay right on top of the direction vector. Now, I was a moron when I was learning Calc 3. Because I somehow thought this vector was the line. I was a moron. I didn't get it. I'm like, because it's a vector, it's a position vector. If you do A plus TD, it's a vector that starts at the origin and points to a point on the line. The line's the collection of points this vector points to. You don't, it's not the vectors, that's not a line. If I swing out all those position vectors, A plus TD, that's not the line. The line is the endpoints of where the vectors point to. Okay, so we've got a position vector and a direction vector. But we also have a point. So let's put a point in the game. Let me just put my point there. Now I'm in back of the camera. How many people think they could find a vector that goes from the origin and points to the point? How many people think they could find a vector that starts at the origin and goes to the point? Like for example, if the point is 217, what would a position vector be that would point to 217 from the origin? What would that position vector be?
(217).
217, the vector 217. And let's just mark that as B. Let's just mark that as B. Okay, so now you draw B. You draw B on the diagram, because you're gonna be the ones deriving this if you have to do this. You draw B. Where is B in the game? Where is B in the game? Draw B. And I'm hoping you drew that vector. I'm hoping you drew that vector. I hope you drew the vector that starts at the origin and then runs up here. I'll mark this as B, the vector B there. That's the vector B. This is A, this is B. Now here's the problem. The vector B, we can't see it real well in two-dimensional space. The line is actually a line, I'm visualizing this, that my line is actually lying underneath my vector B. The green vector is the vector B, and the blue vector is the vector D. So these aren't touching. Could you come up with a vector that would point to the point, but also connect to the line? Could you come up with a vector that could connect your line to your point? Could you come up with a vector that would actually connect your line to your point? You're like, I think I can do that, Dr. Warren. If I look at, here's A, here's B, if I connect my line to my point, what vector would that be? Write down what you think it is. Look at that. Write down what you think that vector would be. And what do you think that vector is? What do you think that vector is, guys? What is that vector?
B minus A.
B minus A. So this is the vector B minus A. Now imagine on Friday, could you find B minus A? I mean, look at the numbers that are on the board. Could you find B minus A? I mean, if you're looking here, if this is A and this is B, how many people are pretty comfortable they can find the vector B minus A that's there? Like, well, Dr. Warren, it ain't bad. It's just this guy minus that guy, this guy minus that guy, and this guy minus that guy. Okay. Now we're in the game. The shortest distance from a point. Let's imagine that I've got my fist here, and I want the shortest distance from my fist to this line is going to be the one that, the line that lies perpendicular. If I think about this, I've got my point, I've got my line, my green is my line. The connection that lies perpendicular, where this makes a right angle, is going to be the shortest distance between that point and that line. So I really want to drop a perpendicular from P straight to the line A plus TD. Now we're finally getting enough information where we can almost start making some progress. Let's call this angle theta. It's the base angle of this right triangle. It's the base angle of this right triangle here. Make D a little shorter. Okay, this is the distance I want. That's the distance I want. It's one of the legs. It's one of the legs of the right triangle. Is it the leg opposite the angle or adjacent to the angle? Is that leg opposite to the angle or adjacent to the angle?
Opposite.
Opposite. So as far as your trig functions are concerned, would it be more naturally connected with sine or more naturally connected with cosine? Sine. The hypotenuse times the sine of theta would be this distance. The hypotenuse times the sine of theta would be this distance. Well, how long is this? If this is the vector b minus a, how long is that vector?
The norm of B minus A.
Norm of b minus a. So this distance that I want is the norm of b minus a times the sine of theta. It's the norm of b minus a times the sine of theta. And you're like, okay, great, Dr. When we're done. All I got to do is take the norm of b minus a and multiply it times the sine of theta. And I'm like, okay, what's theta? And you're like, well, theta is the angle between the line and this vector. Okay, what is it? I mean, here we go. Here's your line. Here's your point. What is that angle? And you're like, oh, crap. I don't even have a calculator. I don't have a calculator. There's no way I'm going to answer this question. I don't even have a calculator. How am I going to possibly answer this question? It's the angle between the line, okay, the angle between D and B minus A. Theta is the angle between D and B minus A. And it's got a sine of that angle. Between the dot product and the cross product, which one had a sine associated with it and which one had a cosine? Which one had a sine and which one, you got a quest coming up. Which one had a sine and which one had a cosine? The dot product had a cosine and the cross product had a sine. So let me just erase this here. Let's see how you're doing with your flashcards. Do not look at your flashcards. You should be staring right at the screen. On the quest, this represents the area of the parallelogram that A and B are sides of, but it's also equal to what? The norm of A cross B is equal to the norm of A cross B is equal to the
Norm of A times norm of B.
the norm of A, the norm of the first vector, times the
Norm of B.
norm of B, then times the
Sine of theta.
sine of theta. In general, it's the absolute value, but that's not going to matter on the test. Sine of theta, sine of theta. I will not burn you on a true false because of an absolute value sign. The norm of A cross B is equal to this. So now let's come over here and look at our two vectors. This is the vector, look at my hand. This is the vector
B minus A.
B minus A. This is the vector D. So over here, this would be like A, this would be B, theta is the angle between them. Now, what if I did the norm of b minus a? What if I looked at the norm of b minus a, that vector crossed with d? What if I looked at the norm of the vector b minus a crossed with d? And I use this flashcard. I use this flashcard that I've got memorized. This would be equal to what? If I did the norm of b minus a cross d, that would be equal to what? Using this flashcard, it would be equal to what?
The norm of B minus A
The norm of b minus a
times the norm of D
times the norm of d
times sin theta.
times sine theta, where theta is the angle between d and b minus a. And you're like, oh, Dr. Moore, this is awesome. This is awesome. And some of you are like, I don't get it. No, this is really awesome. Look, we want this. This is the distance. This is the distance. The norm of b minus a times the sine of the angle between the line and b minus a, or between the line and d. And look, do we have a norm of b minus a? Do we have a norm of b minus a? Do we have a sine of theta? You're like, well, how about this guy, Dr. Moore? How about that guy? No, we don't want him. We don't want him. We don't want him at all. Could I take this guy and move him under here? Could I take this norm of d and slide him underneath the other side? And if I did that, if I divided this guy by the norm of d, which would remove that guy, deadly silence. Awkward pause. Just like I do on dates. Talk, then just shut up. Because you realize I've been talking for so long. Nobody's listening. The right side represents, the right side represents, the right side represents. Norm of b minus a times sine of theta represents.
What is the distance to the line?
The distance from the point to the line. Well, then the norm of b minus a cross d over the norm of d also represents that. Like, whoa, Dr. Moore, wait, one more time. Well, I mean, like, let's think about this for a second. How many people could get b minus a? Like, I mean, look at the numbers in play. How many people think they could get the vector b minus a? Just look up there. How many people think, like, you know, I gave you this line, 131 plus t 462. How many people could get b minus a? If this is the point, and then how many people think they could find b minus a, that vector? I hope the answer is yes. I mean, it's not bad. This vector minus that vector. Who's d? Who's the d vector? Who's the d vector? 462. Could you take that cross product? Could you take the cross product of a vector crossed with another vector? Could you do that? Could you take the norm of that vector? Could you take the norm of that vector once you're done? And could you divide it by the norm of the d vector? Would you rather do that or go angle hunting? Would you rather do that or go hunting for theta? Which would you rather do? Would you rather use this flashcard on the quest, or would you rather go like into a travel Destination America hunting show where you're trying to find the ghost theta?
Flashcard.
The flashcard. Okay, so don't you look at the board. Don't you look at your notes. You look me in the eye. If I asked for the distance between a point and a line, you guys would remember what flashcard on Friday?
Norm of b minus a
Cross D.
Norm of b minus a cross d
Over the norm of D.
divided by the norm of d. Divided by the norm of d. And you're like, well, who's A? I'm like, are you kidding? Are you kidding? Who's B? That's a little bit harder, but it's just the vector that points to the point. It's just turning the point into a vector. It's just turning the point into a vector. Okay, guys, I asked for homework on that. I asked for homework in section. There were questions like that in the homework, in section 12.5, Now again, you're not allowed a calculator. You're not allowed a calculator. So I've got to pick numbers that make this cross product reasonably simple. I've got to pick numbers that make this cross product reasonably simple if you're asked to do this. Now let's say somebody didn't take the time to make their flashcards and memorize their flashcards. How screwed are they as they sit down to try to read or write it? How screwed are they? In a 40-minute quest, Okay. Okay, stand up. Get something to drink, If you don't have something to drink, get yourself some water. Go grab yourself some water.
Dr. Warren,
Yep.
is what we're about to start going to be on this quest?
No, Josh, it's not.
Is the distance just the left side of the equal sign, or is it like the norm of b minus a sine theta as well?
It's just, is that Nick?
No, Cameron.
Cameron, it's just this.
Just one.
The fact that that equaled that, that's why it's the distance, but it's just that. That's what you would calculate on a quest. All right, guys, let's sit back down. Okay, we're now ready to start a new topic. Section 12.5, if you look at the title, it's called Lines and Planes. What have we been talking about?
Line.
Lines. What have we not been talking about? Planes. And in fact, you guys haven't talked about planes much. In high school, did you talk about lines occasionally? Did you talk about lines? And curves and stuff like that, circles, rectangles, but you didn't talk about planes because you haven't lived in three-dimensional space. So draw yourself an XYZ. And put a point in your XYZ space. Just stick a point in your XYZ space. And mark it as P1. And I'll do the same. I'm asking you guys to play, I'll play too. So I'll call this point P1. So my three-dimensional space has enough algebra in it to talk about points. Do you agree? I can talk about a point in three-dimensional space. Now give yourself another point, maybe we'll go over here, and call that P2. Now from Euclid, Dr. Warren, why are you bringing him into this? From Euclid, 2 points determine a, line. And we've talked about that. But now let's pick a third point. Let's call it P3. Now don't get angry with me. How many people think they could find the shortest distance between this point and this line? How many people think they could find the shortest distance? How many people think they could find the shortest distance from that point to that line? What flashcard would you use? Oh, Dr. Warren, I hate you. What flashcard? Don't you look at your notes. What flashcard would it be? Norm of B minus A cross D divided by the norm of D. Okay, so hopefully you guys could find a position vector, start at the origin, go to P1. You could find a direction vector, the difference between P1 and P2, and then you could just figure out your flashcard, draw a position vector there, and do that. But also with Euclid, 2 points determine a line, so there would be another line. and there would be another line. In fact, if I just connected those, I would have 3 lines. Now, what's unique about these 3 lines in my 3-dimensional space? What's unique about these 3 lines as they sit here in 3-dimensional space? I've got these 3 points sitting anywhere in your room, and I'm asking, what's unique about these 3 lines sitting in 3-dimensional space? Well, one thing is they intersect. But what else could you say is unique about them? They all lie in the same. They all lie in the same. They all lie in the same plane. Another point, another thing from Euclid is 3 points determine a plane. Write that down. 3 points determine a plane. Okay, this is what we have so far. A plane is equal to, when I write that down, you should hear. When I write that down, we're going to talk about what next? A plane is a, when you see that, you should be afraid. When you see that, a plane is a set of all the points x, y, z, all the points in 3-dimensional space, that lie on the plane containing P1, P2, and P3. It's the set of all points x, y, z that lie on the plane containing the points P1, P2, and P3. And then somebody who's a good mathematician would be like, whoa, man, you can't use the word, you can't define the word plane with the word plane. And you're right. So we don't have anything. Yet. We need to do better than that. High school, when you see that, you say what? In high school, you see that, you say what? They beat this into you. You see that, you say, yeah, y equals mx plus b. It's a line. It's a line. And you're like, okay, but this is what they don't say. They don't really say, they should say this. It's a collection of all the points in the plane that satisfy that equation. That's what they don't say. And so kids don't think about it as a set of points. They just memorize y equals mx plus b. B's the y-intercept, m's the slope, line. They don't think about it as a collection of points that satisfy this equation. Now I get it. In 7th and 8th grade, kids don't even know to wear deodorant. They don't even know where deodorant. You walk into a middle school classroom, oh my gosh, the smell is unbearable, especially after gym class. They come back from gym class. I don't think they smell each other because their smells like balance each other off. It's kind of like some law in physics that this stink versus that stink. It's like when kids are in the pool. They're all pissing on each other, but it's like, they don't feel it because they're. So I'll stop. Okay, back. In the same way, we've got to think about a plane as a collection of points. Now the question is, what does the equation of a plane look like? And that's where we're going. Okay, stand up again. Because the moment Josh asked, Will this be on the quest too? Some of you guys decided, I'm shutting my brains off right now. I'm going to turn into a scribe. I'm just going to scribe what Dr. Warren writes on the board. I'm not listening, I'm not listening, I'm not listening. Okay, sit back down. Do I say a lot of words when I teach? Do I say a lot of words? Why do I say the words? I could just be a mute and just write stuff on the board. But why do I say words? I
So
can't
we
give
can interact with you.
So yeah, you can interact. I try to put in little details within the words. But what I've learned is that, like me, my students have a hard time doing multitasking. They can write or they can listen. But it's hard to write and listen. But guys, this is an essential skill. Look at me. This is an essential skill as you move on in life. As you get married, you must learn how to listen and do something else. And I mean really listen, not just I've had a failed marriage. And a lot of it was because I didn't listen. And I still don't listen very well. And I know that doesn't surprise anybody. Everybody who looks at me is like, yeah, Dr. Warren, I can see that. I believe that. I believe you don't listen very well. Okay. Let's try to come up with the equation of a plane where we're given 3 points. You're like, well, Dr. Warren, that sounds pretty tough. No, I know it does. So I'm going to erase my drawing again. And I've got my 3 points. P1, P2, and P3. Okay, now, how many people, if I gave you 3 points, 3 sets of 3 real numbers, could find position vectors to all 3 of those points? How many people think they could find position vectors that would start at the origin and go to all of those points? So let's draw those in. I think you guys could too. I'm going to draw this first one as A. And then I'm not going to be real clever. I'm going to mark the second one as, what do you want to call that vector? B. And my third vector, I don't want to run over A, as C. Okay, Dr. Warren, I'm with you. Now let's get 2 vectors that actually lie on the plane. Let's get 2 vectors. Let's try to find 2 vectors that we can actually say would lie on the plane, at least the way we draw on them now. I want to find 2 vectors that would lie on the plane. And I'm going to draw them. I'm going to draw the vector that starts at the head of A and runs to B. And I'm going to start with another vector that lies at the head of A and runs to C. Label those in terms of the letters that are already in play. Label those. You've got a vector that starts at A and goes to B, and a second vector that starts at A and goes to C. Okay, what did you label that vector? What did you label that vector? What was that vector right there? This vector right here, guys. What was this vector?
B minus A.
B minus A. Very good. This is the vector B minus A. So let's mark it as B minus A. I know I'm drawing small. I apologize. I drew my figure too small. This is B minus A, but you get it right down on your diagram. The vector that goes from A to B. And this vector here would be, that vector here would be C minus A. So mark that vector as C minus A. Let me go get a marker. Let me go get a magic marker. I'm not so much going to worry about what's drawn on here, but imagine that I've got this point, which is right here. I get this point which is right here. I've got some other point, maybe that's P2, and I've got this other point over here that's P3. So the whole down this thing down here, this is P1. Over here's P2. And this is P3. Now the vector A is starting at the origin. The vector A is starting down here at 0, 0, 0, and running to that point there. So it might look something like this. It might look something like this. Similarly, the vector B is running to this point. And the vector C is running to that point. And I can almost imagine these vectors as kind of supporting my plane from the origin. You know, if I was welding those on there, I'd have this really cool plane flying through, and kids would be walking underneath it, enjoying the shade that my plane would throw on them. Well, I guess I'm throwing shade on them. Maybe they don't want that. Okay, so I'm throwing shade on them, but I'm supporting them. Now the vector B minus A would be the vector lying on the plane that would start here at A and end over here at B. So it might be a vector that's like this. The vector C minus A, I don't know, that didn't sound good. The vector C minus A would be the vector that points like this. Could you find a vector that's perpendicular to the plane? Do you think you could find a vector that's perpendicular to the plane? And let me kind of explain why. If I could weld a vector that's perpendicular to the plane, if I could weld it, first, I mean, it better be a good weld, because this is a strong lever arm. I could easily snap this puppy off. But if I have a vector that's welded perpendicular to this plane, let's imagine that it's at A. It's perpendicular. And then I put a ball joint. Dr. Warren, what the hell are you talking about? I put a ball joint at the head of A, so I can move this. It just rotates around A. Do you see how this vector, if I put a handle on it, controls the plane? If I put a handle on this, this controls kind of the direction of where the plane sits in three-dimensional space, how it flies through three-dimensional space. We call this vector that points perpendicular not the direction vector. We don't want to get confused with a line. We call it the normal vector, and it's the most important vector related to a plane. A normal vector is just like a direction vector. It directs the plane, but we call it the normal vector. Now come over to my drawing here. Come over to my drawing. Let's lay in the plane now. It's going to be the plane is going to be the thing that connects. It's going to be the thing that this vector lies in B minus A, and this vector lies in C minus A. Could you find a vector that's this perpendicular to the plane? Could you find a vector that's perpendicular to the plane? Because it would be really useful if we could. So imagine you got this. Here's a vector A. Here's a vector B. And I want a vector that goes perpendicular. Any ideas? Any ideas, guys? Any ideas? I've got a vector A, and I got a vector B, and I want a vector that's perpendicular. Any ideas? Any ideas, guys? Any ideas?
A cross B.
A cross B. So it's not A and it's not B, because A and B aren't in the plane. A and B are not in the plane. They point to the plane. But which two vectors are in the plane? Which two vectors are actually in the plane itself? I mean, I know it's hard. You haven't thought about planes. Which two vectors lie in the plane? Which two vectors lie in the plane? B minus A and
C minus
C minus A. How could you find a vector that sits perpendicular to the plane?
Take the cross product.
Take the cross product. So write that down. Use n, little baby n as a vector. Little baby n as a vector is equal to little baby n as a vector is equal to B minus A cross B minus A cross C minus A. That's going to be a really important vector. Now I've got a lot of stuff drawn over here, but I'm going to try to draw this in here. Give me your hands, give me your hands, give me your hands, give me your hands. Let's karate chop onto our B minus A, and let's swing it towards C minus A. Let's swing it towards C minus A. B minus A cross C minus A. Does the vector point up or down from the plane? Does the vector point up or down from the plane? So let's try to draw that. I'm going to try to draw that in there. It's perpendicular to the plane. And so this would be n, which is equal to B minus A cross C minus A. And Dr. Warren, I could never do this. And I'm going to tell you, yeah, you can. It's just a lot of notation. Dr. Warren, I'll never be able to do this. No, this isn't. If I gave you 3 points, like give me a point. Give me a P1. Give me a P1. Any P1.
3, 6, 8.
3, 6, 8. Give me another point.
4, 2, 5.
4, 2, 5. Give me another point.
6, 9, 2.
6, 9, 2. Like Dr. Warren, can you put that on the quest? Could you put that on the quest? Just say, give me a point. Could you do that? Could you just say, give me a point? I mean, wouldn't that be a nice question to have on a quest? Give me a point, okay? And then, I no matter if I did that, some student would leave it blank because they'd be confused. And I know that, and I'd be like, oh, this was supposed to be an easy one. But it's so vague that I think they'd be like, well, what the hell does he mean? Give me a point. Could somebody give me a position vector that points to this point? Could somebody give me a position vector that points to that point? That would be the vector A. Could somebody give me a position vector that would point to that point? And so that would be the vector, I mean, it's not hard. That would be the vector
3, 6, 8.
3, 6, 8. Similarly, a vector that points to this point, the second point, my vector B would be
4, 2, 5.
4, 2, 5. Now I'm convinced everybody can get C. 6, 9, 2. How many people could do that? How many people could at least do that? How many people? Raise your hands. At least I'll know you're right. They're good, David. I would right. So now, how many people think they could get the vector B minus A? I mean, if this is B and this is A, how many people are like, Dr. Warren, I think I could get that vector. I think I could get the vector B minus A. Now, what if I said, oh, give me the vector C minus A? Give me the vector C minus A. Again, you're like, Dr. Warren, it's the same thing. Can you take the cross product of two vectors on Friday? Or are you going to have to take several cross products of vectors? Yes. It's not hard. It's a little bit time consuming. The easiest way is to do the determinant, I think. I mean, do the determinant I, J, K and throw them in there. But I don't care how you do it. It's this n is just the cross product of your two difference vectors. I'm not gonna write it down because we're just working towards an equation right now. I just want to say, even though this is a lot of writing,